right, everybody, we're ready to get started. How's everyone doing today? Excellent. Welcome to the Morrison Planetarium. My name is Mary. I'm going to be your presenter today for our tour of the universe. And this is one of my favorite shows that we do here in the planetarium because it's a bit different than the other shows that we have throughout the day. Most of the shows that we do in here are pre-recorded movies, essentially, with a short section where a presenter can update you on a particular topic. This show, however, is completely live, so I'm going to be our pilot as we fly around the universe today. We're going to start out at Earth, we're going to zoom out as far as we can out into space, and we'll come back safely home at the end of our journey. And I'll be controlling everything we see on the dome above us from our pilot's booth, which is at the very top of the room up there. So in order to get started, I do have to head all the way up the stairs to our pilot's booth, and on my way up, I've got a few quick planetarium housekeeping rules to go over. First of all, please no eating or drinking while you're in the planetarium today to make sure we're keeping our theater nice and clean. If you have a cell phone, a camera, a tablet, anything at all that could give off light or sound, both of those can be very distracting in here, so we want to make sure that those are all put away during the whole show. For your safety in this dark theater, we highly recommend staying seated throughout the entire show, but if you do find that you need to leave early for whatever reason, the exits are at the top of the stairs on either side. Last but not least, this can create a rather immersive experience, so if at any point throughout the show you feel any dizziness, any motion sensitivity, just go ahead and close your eyes for a few seconds, and that will remind your brain that you're just sitting in a chair in a planetarium, not actually flying around in space. So without further ado, go ahead and sit back, relax, give me a minute to move into our pilot's booth, and then we will get started. All right, so we are starting our tour of the universe today, relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And I always like to start us out at the International Space Station because it gives us a little bit of perspective on the incredible distances that we're going to see today. Because today we're going to see things like how far has our human influence gone out into space? So we'll see things like how far our human beings have traveled, how far our spacecraft have traveled, how far anything we've sent out into space has traveled. And we are going to travel much, much farther than that, way out into the farthest reaches of our known universe. And a really cool thing about what we're doing today is that we're doing all of this with a software called OpenSpace, which is a free open source software developed by NASA, folks out at the American Museum of Natural History, folks out in Sweden, so several different places, and we're partners with them as well. And it's all based on real data. So all the places we're going to visit are based on actual observations and data of the different places that we're going to go to today. So we're actually seeing the International Space Station here in its real location right now. So this is where it is, above the ocean somewhere. As we zoom out, we'll get a better idea for where we are right now. And the International Space Station, this is as far as humans travel out into space right now. You can fit about 10 or so astronauts on the International Space Station at any one time. And people have been living up there for a while now, about 20 years or so. But not the same people for 20 years. They do swap out every few months. And the longest that any one particular person has lived there was about a year. And I'll bring up a yellow line as we zoom away from the ISS so we can see where it is orbiting around us. And they're orbiting really fast. It only takes about 90 minutes for them to orbit us once. And if you ever get a chance, you should look up when the International Space Station is going to pass overhead. You can look online and see exactly what time it's going to pass over your area. Just look for Spot the Station is what will show you what time it's going to pass over. And when it does, it just looks like a pretty bright star moving pretty quickly across the sky. So it's actually pretty easy to be able to spot. Oh, looks like it's about to head over to North America right now. It's heading towards Canada. But we're not going to stop here at our lovely home planet Earth for very long. And really, we're not going to stop anywhere for very long on our journey today because we have a long way to go. So we're going to go at a pretty quick pace here. So already we're going to go away from the Earth and focus on our next stop as we go away from our planet today. We're going to focus now on the moon. And the moon is as far as humans have traveled out into space at all so far. The Apollo astronauts came out here back in the 1960s and 70s. And we do have plans to send people to the moon again. The Artemis program, for example, with NASA is planning to send people back to the moon. But even though this is as far as we've gone, it's our closest neighbor. And even though it is our closest neighbor, it is pretty far away. It took over 2 days for the Apollo astronauts to get out here, and it's about 250,000 miles away from us. And here at the moon is where I like to introduce an idea that I'll be using throughout the rest of the show to talk about how far we've gone. Because already we're up to over 250,000 miles here. So as we see distances later, we're going to see millions, billions, trillions, or more of miles and kilometers. So if I tell you how far we've gone in terms of miles and kilometers, it's not going to make much sense pretty quickly because the numbers are just too big. So instead, we're going to try to think of things in terms of the speed of light. If you could imagine moving the fastest speed we know of in the entire universe, the speed of light, it would have taken us about 1.5 seconds to get to the moon from Earth. So we can say that the moon is a distance of 1.5 light seconds away from us, because that's how long it takes for light to travel here. So pretty quick, only about as long as it took us to fly over here in OpenSpace is about how fast we would get here if we were traveling at the speed of light. But let's zoom out here, and I'm going to bring up some more lines to show us where there are things in our solar system. So I'm going to bring up some blue lines here to show us the orbit of the moon, as well as the orbits of the planets in our solar system. And once we zoom out a little bit and we see some of the closer in orbits, I'm going to refocus on the very, very center of our solar system, the closest star to us, the sun. There we go. And the sun is about 8.5 light minutes away from us. So to travel there, traveling at the speed of light would take about 8.5 minutes. And there's a couple of ways I like to think about that. One way you can think about it is that if the sun just disappeared, we wouldn't know about it for 8.5 minutes. Thankfully, though, there's no reason why the sun would just disappear. You don't have to worry about that too much. Another way I like to think about it is that if you walk outside and you look at the sun, first of all, please don't do that. Please never look at the sun. It's very bad for your eyes. But if you were to look at the sun, that's how the sun looked 8.5 minutes ago, not how it looks right now. And within these few light minutes of distance, we are seeing the orbits of the smaller rocky planets in our solar system. Closest in is Mercury. Then we've got Venus, Earth, and Mars. Then we got a pretty big gap here, and then there's Jupiter, Saturn, Uranus, and Neptune. But that big gap in between Mars and Jupiter, that is not totally empty space, despite how it is looking to us right now. There are actually a lot of objects in between Mars and Jupiter. Let me bring those up for us, make them much, much brighter than normal so we can see them more easily. And those are the asteroids, well, some of the asteroids in our solar system. So this is where we find the asteroid belt, where we find a lot of the smaller rocky objects in our solar system. And we think there are roughly 1 million or so asteroids in the asteroid belt. But this is not the only place we find asteroids. We find asteroids in a lot of different places throughout our solar system. But this is where a lot of them are, is here in between Mars and Jupiter. And I'll bring up an orbit of one other object, though, in the asteroid belt that we consider to be something other than an asteroid. It's considered to be the largest asteroid, but also a dwarf planet in our asteroid belt. Right over here, that blue orbit we see inside the asteroid belt is Ceres. Now, if you've never heard of Ceres before, don't feel bad. Often people haven't heard of Ceres before, but it is a dwarf planet, and it has then the same name or distinction as another much more famous object farther out in our solar system. I'm also going to bring up the orbit of Pluto. Now, I sometimes get people still wondering about Pluto and asking me questions about Pluto, wondering things like, what happened to Pluto? Did Pluto get kicked out of the solar system? Did we blow up Pluto? Why do you hate Pluto? But I'm here to tell you, I don't hate Pluto. I actually really like Pluto. I think it's a very interesting place in our solar system. And it's a wonderful place that we got to visit with a spacecraft. We sent out a spacecraft to it just a few years ago, which we'll look at in a minute where that spacecraft is. But there is a reason we don't call it a planet anymore. It's been a few years now that we haven't called Pluto a planet. And the big reason for that is where it is in the solar system. Let me bring up some more lines here to show us where there are some objects farther out in our solar system. This is where we find the Kuiper belt, which is kind of like an icy, bigger version of the asteroid belt farther out in the solar system out here. And we did not know about the Kuiper belt until fairly recently. In the late 90s and early 2000s is when we started to get good enough telescopes to be able to track some of these smaller icy objects that are farther out in our solar system. And as we started to find a lot of these, some of them were around the same size as Pluto, and a lot of them were around where Pluto is. So we had a conundrum on our hands. Do we come up with, or do we call some of these planets, or do we come up with something else to call them? What do we do? So back in 2006, a group of astronomers got together and decided, okay, we're going to have 3 requirements for a planet. Number 1, a planet needs to orbit the sun. Number 2, a planet needs to be massive enough that its own gravity has pulled it into a round sphere shape, so it needs to be round. And number 3, it has to have cleared out its path. It has to have a relatively cleared out orbit. Pluto did not fulfill that 3rd requirement because Pluto is part of the Kuiper belt out here, far out in our solar system. So it was kicked out of the Planet Club back in 2006. But at the same time, they came up with a new category of objects called dwarf planets, which are big enough to be spheres, orbit the sun, but have a bunch of stuff in their orbits. And so now Pluto is the largest dwarf planet in our solar system. So some people were sad about this, but I think of it as a positive story where we learned more about our solar system, and Pluto is now the king of the dwarf planets, which is kind of fun. And now that we're out here by Pluto, let's check in with how far we've gone. So we were looking at a distance of 1.5 light seconds to get to the moon, the farthest the humans have traveled out into space so far. It was 8.5 minutes to get to the sun if we were traveling at the speed of light. And now out here by Pluto, we're looking at distances of light hours. To get from one side of Pluto's orbit to the other, that would take us roughly 9 hours if we were traveling at the speed of light. And this is a good spot to check in with any sort of human stuff that we have out there in the universe, because we can now see how far our spacecraft have traveled. So these 5 yellow lines here are to show us how far the farthest spacecraft we've sent out have gone. So these are showing us Voyager 1 and 2, Pioneer 10 and 11, and New Horizons, which went out to Pluto back in 2015. And these are the farthest spacecraft and some of the fastest spacecraft we've sent out. Some of these have been traveling for a while, since the 1970s. But even so, even though they've been traveling for a very long time, none of them have gone as far as light can travel in a single day yet. So we're still only looking at light hours at this point. We haven't quite gotten out to light days. And this is an interesting kind of gray area of space that we're looking at here, where we can ask the question, are we still in our solar system, or have we left our solar system? And that's a little bit of a tricky question. There's a lot that goes into our solar system. There are planets, there's the sun's gravity, the sun has a magnetic field, it's got asteroids and comets that are going around it that can go out really far sometimes. So it's a little tricky to try to determine exactly where our solar system begins and where our solar system ends. But right around here, you can see the sun adjusting before we dimmed down the sun so we could actually see the other things in our solar system better. But now we're looking at the sun at its true brightness. So this is how bright it would be if we were really this far away out in space. And right around here, you'll notice we are starting to fly past other stars. And when we start to fly past other stars, well, there's no question. We are definitely outside of our solar system, and we are now in interstellar space, the space in between stars. Now to check in real quick with how far we've gone at this point, we've bumped up in distance quite a bit, because to get to the closest star to us outside of our solar system would take us a very long time, even if we were traveling at the speed of light. At that fastest speed, it would take us at least 4 years to travel to the closest star out here. So we've gone from a few hours to go across a good portion of our solar system. Now we're looking at several years to even get to the closest object outside of our solar system. And everything we're seeing from here on out, we're seeing these objects not because we've traveled there and gone and like snapped a picture, because we've already seen how far our farthest objects have gone, the spacecraft have gone. So everything we're seeing from here on out is because light from these objects has traveled to us, and we are able to see them from here on Earth or out in space with our telescopes that we have. But something really cool about a lot of these stars that we're looking at here is that we've discovered that these stars are often, or most of the time, not alone. Many of these stars have what we call exoplanets, planets that are outside of our solar system. And every single one of these blue markers here is showing us where there is an exoplanet. And many of these dots here are showing us stars that have multiple exoplanets, just like we have multiple planets too. And we've only been finding these since the mid-1990s, and we're already up to over 5,000 that have been found so far, and many that are being waited to be confirmed as well. And right around here, where we're seeing a lot of the kind of nearby exoplanets, this is our last chance to check in with any sort of human influence that we have out in space. Like I said, I've already seen how far the farthest objects we've sent out have gone, but there's something else that we're sending out into space all the time, and we can see where that edge of that thing is with this sphere here. This is what we sometimes call the radiosphere, or it's sometimes called our technosignature is another name for it. And that's because we're sending radio signals out into space. And we've been sending radio signals out into space for quite a while, since about the 1930s or so. And all of our radio signals that are traveling out into space, they're traveling at the speed of light. So they've been traveling for roughly 90 or so years. So this sphere here is about 90 light years away from us in any direction, is the farthest that our signals could have gone by now. And if you look carefully, you can see there are a bunch of exoplanets inside of the radiosphere, so who knows, maybe there are some aliens listening to our radio shows. That would be cool. Unfortunately, no luck finding aliens yet. There are scientists that are searching for them, though, all the time, so hopefully we'll find one, or find some at some point in the future, maybe on one of these exoplanets that we're seeing around us. But let's keep going, because we're still in our galaxy, the Milky Way. We haven't even left our galaxy yet. We still have a long way to go. And I'm going to turn off the exoplanets as we zoom out, but leave on the radiosphere. See how long you can spot it as we zoom farther and farther away. And in a moment, we'll see a nice model of what we think our galaxy, the Milky Way, would look like if we could go outside of it. So like I mentioned, we haven't actually traveled this far. We haven't sent a spacecraft or anything out here to go and snap a picture of our galaxy for us. So this is not a picture of our galaxy. But based on what we do see from our position inside of our galaxy, and based on what we see from other galaxies, we've got a pretty good idea of what we do think it would look like if we could step outside and take a picture. So this is a nice model of what we think our galaxy does look like from the outside. And our galaxy is huge. We're now looking at distances of thousands of light years. If you wanted to travel across the Milky Way from one side of the galaxy to the other, the long way, that would take you at least 100,000 years traveling at the speed of light. And this contains hundreds of billions of stars. We think maybe a few 100 billion stars, and probably hundreds of billions of planets too. But if you can still see the radiosphere, that little tiny dot on the bottom left over there, that is how far anything we've sent out into space has gone, that little teeny tiny area. But we're not going to stop here either, because our galaxy is just one galaxy out there in the universe. As we zoom out farther, now every dot we're seeing, these are no longer individual stars. Instead, every single dot we're seeing is another galaxy, and every single one of those galaxies has millions or billions or sometimes even trillions of stars. And the colors of the galaxies we're seeing here are kind of interesting. There's lots of different colors that we're looking at. Now, those aren't the actual colors of those galaxies, though I do think it would be fun if it looked like cosmic Skittles out there in the universe. But no, we've color-coded them based on a variety of different things. Things like what survey was used to map out that galaxy, so what telescope or group of people mapped it out. And things like density and stuff, too, plays into what colors we've chosen. But this is a real map. People have mapped out where these galaxies are relative to us. So this is where we've seen them, and we've tracked where they are and how far away they are from us. And since it is a real map, there's a couple of things that look a little bit strange, especially as we get farther and farther out here. For one thing, the shape that the galaxies seem to form is going to look a little odd. It's going to look sort of like a butterfly or bow tie or something like that. I'll get a nice angle for us here so we can see that more easily. We rotate around a little bit. Now, the universe is not shaped like a butterfly, though I do think that would be fun. The shape we're seeing here is because of our galaxy, the Milky Way. So these gaps that we're seeing on the top and the bottom here, it's not that there aren't galaxies over in those directions. We think there are just as many galaxies over in those directions as there are to the left and the right here. But our galaxy's in the way. There's gas and dust and stars in our galaxy, and when we try to look over in the direction of those gaps, our galaxy's blocking our view, making it so we can't see the galaxies that are over in those directions. So there are even more galaxies than this, but this is just what we had been able to see and map out so far. And we're looking at things that are incredibly far away, and also we're kind of looking back in time when we look at these objects that are really far away, because this light takes so long to get here that by the time it travels to us and gets into our telescopes, we're seeing the light of these objects as they were in the past, not how they look right now. So if you remember at the beginning of the show, I said if you look at the sun, which again, please don't look at the sun, but if you looked at the sun, that's how the sun looked 8.5 minutes ago. Well, this is what our universe was like billions of years ago. So we're looking back in time billions and billions of years. And because of that, that means there's only so far that we can go. There's an edge to everything we can see in our entire universe. And that edge of everything we can see will show up in just a moment here. It's going to be all over the dome. Very, very obvious. This is what we call the cosmic microwave background. Now, the cosmic microwave background, if you walk outside tonight and if you look up at the sky, if it's a nice clear night out, you're not going to see this anywhere where you look in the sky. Thank goodness. If I looked up and saw orange everywhere, I would be scared. But if you looked up at the sky with microwave vision, if you could see the microwave part of the light spectrum, which is a lower energy form of light that our eyes can't see, but our telescopes can, you would see this every single place you look in the sky. And that's because we're looking back in time to very early in our universe. This is a few 100,000 years after when the Big Bang would have happened, when light was first able to go out in all different directions and expand out into space. So before this, everything was in a smaller, hot area and light couldn't really go anywhere. It just kind of kept running into protons and things that were around at the time. But this is the moment that things cooled down and expanded enough that light was able to escape and just spread out and go out in all different directions. So an easy way I like to think about it is that this is the baby picture of our universe. This is the earliest light that we can see. And since this is the earliest light that we can see and the farthest that we can see out in space, that means, well, We can't really go any farther. So to end our journey today, we are going to head back home. I won't leave you stranded out here far out in space. But keep in mind, if we were really this far away out in space, and if we were really traveling at the speed of light, the journey home would take us over 13 billion years. But thankfully, we're in the planetarium, so it should only take us a couple of minutes. Here we go. And as we fly back home, one last thing I do like to leave folks with is that all of this that we've been looking at, stars, galaxies, cosmic microwave background, asteroids, dwarf planets, everything we can see, that is a very, very small amount of everything we know to be out there. There are some mysterious things in our universe, things like dark energy and dark matter. Dark energy is some mysterious force that is causing space itself to accelerate as it expands out in all different directions. There's dark matter, some mysterious substance that doesn't seem to interact with light at all, but we see a lot of evidence of it, especially at the edge of galaxies and stuff. And we call these things dark energy and dark matter because we're not quite sure what they are. But we do know that they make up roughly 96% of our universe. So all of this that we can see, that is a tiny percentage of everything we know to be out there. And sometimes that makes people feel kind of small and uncomfortable. And I agree, sometimes it makes me feel a little uncomfortable too. But one way I like to think about it is that, well, sure, we are this one tiny dot in this gigantic universe, but look at all of this that we have found so far, almost entirely by just looking through telescopes. And there's a whole lot more to discover and a whole lot more to learn about, and that is pretty exciting if you ask me. But even so, I always breathe a little sigh of relief when we get back to our own familiar home galaxy, the Milky Way, and we can see our little human realm in our radiosphere there, where once we pass that, we'll have about 90 light years left to go. Let me turn that off as we zoom in. And in a moment, we'll see our closest star to us approaching, the very center of our solar system, the Sun. And as we re-enter our solar system, we'll see those farthest spacecraft that we sent out, the farthest objects we put out into space. And we've done all of this from our own little home planet, the third planet from the Sun, the only place in all of this where we have found life at all so far, which is pretty incredible to think about too. And we are back home. Hooray! So with that, I want to thank you all for joining me today for our tour of the universe. I hope you enjoyed flying around in space with me, and I hope you will all enjoy the rest of your day. Thank you so much for coming.